Hey everyone, welcome back to The Explainer. Today, we're diving straight into a massive breakthrough in artificial intelligence that is literally flipping how we think about machine reasoning on its head. You see, the ability for a machine to actually reason about the future is arguably the single biggest hurdle in AI right now. Whether we're talking about a robotic arm trying to handle delicate objects without crushing them, or a self-driving car trying to navigate a crazy, unpredictable city intersection, an AI has to understand the physical consequences of its actions before it actually makes a move. Well, a new paper just dropped from FaceMind Research Asia called Looped World Models, and it introduces a radically different way for AI to think and simulate that future. We're going to unpack exactly how this unbelievably efficient model is coming out of nowhere and completely outperforming industry titans. So just to set the stage, what exactly do we mean by a world model? Basically, it's an AI's internal engine for predicting how an environment evolves over time in response to specific actions. Think of it as the foundational architecture that allows embodied AI to essentially dream and plan. It's literally how the AI imagines the physical and logical consequences of what it's about to do, way before committing to it in the real world. Sounds awesome in theory, right? But here's the catch. The core challenge is what happens when an AI tries to predict too far into the future. I mean, what happens when that simulated dream has to cover a really long sequence of complex physical events? Like, say, a robot trying to navigate a messy room for 20 straight minutes. Spoiler alert, it usually falls apart completely. And that brings us to our first major hurdle, what we call the simulation dilemma. It's basically a trap that researchers have been stuck in for years. Conventional models face two massive, fatal flaws when they try to simulate over long horizons. On one side, you have compounding prediction errors. Because these models predict step by step, a tiny microscopic error at step 1, maybe it miscalculates the angle of a bouncing ball by a fraction of a degree, turns into a total reality-breaking hallucination by step 50. The whole trajectory just degrades exponentially until the simulation is useless. But on the flip side, if you try to fix those errors by making the model deeper and heavier, which honestly is the standard brute force approach we see today, you slam right into prohibitive inference costs. The compute power needed just skyrockets and becomes completely unmanageable for real-time systems. You essentially have to choose your poison. You either get a broken, hallucinated dream or a completely bankrupting compute bill. So how do we break out of this trap? Well, enter Looped World Models, or LoopWM. Take a close look at that central loop in the architecture diagram. If you look at standard transformers, they're kind of like a massive, rigid assembly line. Data passes through layer after layer after layer, and that requires a massive amount of distinct parameters at every single stop. LoopWM completely flips that script. It uses a parameter-shared recurrent transformer block. So instead of building this incredibly deep assembly line of unique, heavy layers, it just reuses a single shared set of parameters in a continuous loop to refine the state. It's so smart. It actually breaks down into 3 really intuitive stages, creating this beautiful continuous flow of data. First is the prelude. This just takes the observation and the planned action and processes them into an initial signal. Then, stage 2 is where the absolute magic happens, the recurrent block. Notice the loop here. The shared transformer refines that state over and over, continually polishing the data without needing any extra parameters. Finally, stage 3 is the coda, which just hands us the final projection of the hidden state once that refinement is totally complete. Now, you might be wondering, wait, if data just keeps looping through over and over, won't the numbers eventually spiral completely out of control and explode? It's a totally fair question, but the researchers solved this with something called a spectral stability guarantee. Essentially, they introduced a mathematical bounding box, specifically a continuous time negative diagonal matrix, if you want to get technical, that ensures the eigenvalues stay bounded. In plain English, this is the secret sauce that guarantees these loops remain perfectly stable no matter how long they run. The data can spin through that loop 100 times, and it will never trigger those awful compounding errors that destroy conventional simulations. Just let this number sink in for a second, because LoopWM reuses its parameters in that perfectly stable loop instead of just mindlessly stacking new ones. It achieves up to 100 times parameter efficiency compared to fixed-depth approaches. That is a staggering number. It completely decouples computational depth from parameter count. What that actually means is a tiny model can now perform the deep, intensive reasoning that normally requires massive server farms, and it can do it on standard accessible hardware. But it actually gets better, which brings us to the power of adaptive computing. Think of the AI kind of like a master chef. Some tasks are quick and easy.
Others need constant tasting, adjusting, and intense focus. Fixed-depth models treat every frame the exact same way, allocating massive computational effort even when nothing's happening. But Loop WAM is adaptive. If it's simulating something simple, like a ball just flying through empty air, it might just run one single loop iteration. Boom, done, moving on. But if it hits a complex transition, like a multi-body collision with pieces flying everywhere, it dynamically scales its depth. It spends heavy compute through multiple loop iterations only where it absolutely needs to.
The mechanics behind this are super elegant. The model uses a lightweight exit gate, basically a simple multi-layer perceptron, to constantly check a confidence threshold. As soon as the model is mathematically confident in its simulation of that specific step, it literally terminates the inner loop and exits early. Over a long rollout, this dynamic early exit massively slashes your aggregate inference costs. It's just a brilliant way to preserve computing power for the moments that truly demand it. Okay, so that adaptive compute is their first secret weapon. Let's look at the second one, which radically changes how the AI visualizes the future. We call this deferred decoding. So, traditional models use step-by-step decoding. Imagine walking to the grocery store, but forcing yourself to perfectly memorize and visualize every single blade of grass along the sidewalk before taking your next step. It's exhausting, right? That's what standard AI does. It wastes massive compute generating visual pixels at every intermediate step. FaceMind's new paradigm is deferred decoding. The AI encodes the starting info, thinks continuously in a conceptual latent space, and then decodes only the final state at the very end. So instead of doing all that extra work, here's the new flow. First, the model injects a sequence of planned actions. Second, it advances the latent state entirely in a hidden continuous space, using that looped architecture we just talked about. And finally, step 3, it decodes the observation and the reward only at the terminal step. This laser focuses the AI entirely on long-term structure and logical reasoning, rather than wasting precious energy drawing visual trivia for intermediate steps that honestly just don't matter. All right, so we've got this highly efficient, roughly 1 million parameter looping model that skips all the unnecessary visual rendering. How does it actually stack up against the heavyweights? Let's look at some David versus Goliath results. Take a look at these numbers from the rigorous Science World dataset. We're putting the tiny Loop WM sitting at just around 1 billion parameters up against Claude Opus 4.6 Max, a literal Goliath that is over 100 times larger. And it's not even close. Across the board, exact match score, token F1, Blue 4, the compact looped model crushes the Goliath. Look at that exact match score, 68.4% versus 47.2%. It's a profound leap in capability, generated from an absolute fraction of the hardware footprint. And if you want to see an extreme outlier, check this out. On the highly complex lifespan task in Science World, Cloud Opus 4.6 Max, with all of its massive computing power, scored a flat 0%. Those compounding errors we discussed earlier completely derailed it. Loop Abe W, it achieved a perfect 100%. The ability to stably loop and refine a thought without those compounding errors makes a night and day difference when we're talking about long horizon reasoning. And just to be clear, this wasn't some weird fluke. Over on the AlphaWorld dataset, which is a text-based environment, LoopWM totally confirms its dominance. It achieves 51.6% exact match, ranks first overall in Blue metrics at 71.6%, and easily dominates Qwen 3.5 Flash across the board. The stable, adaptive performance is just remarkably consistent, regardless of what specific environment you drop it into. So, what's the big picture here? Let's talk about this new frontier in AI scaling. There's a quote directly from the researchers' paper that absolutely nails it. They write, Loop WM establishes iterative latent depth as a previously unexplored and highly effective scaling access for world simulation, orthogonal to both model size and training data. For years now, the AI community has pretty much assumed the only way to get smarter models was brute force, make them exponentially bigger or feed them mountains of more data. This paper proves there is a third way, iterative depth. Letting a compact model loop and refine its thoughts is a total paradigm shift. It means we don't necessarily just need bigger data centers anymore. We have a significantly smarter way to compute. Which leaves us with a pretty mind-blowing question to chew on. If a 1 billion parameter looped model can step into the ring and definitively outclass a 100 times larger Goliath today, what is highly efficient resource-constrained AI going to be capable of tomorrow? When we finally decouple raw intelligence from massive parameter counts, the potential for robotics, mobile edge devices, and real-time planning just explodes. It's a game changer.
Thanks for joining me for this explainer, you guys. Keep your eyes on looped models. We're literally just seeing the beginning.